And for the people who just joined, thank you. And we have a lot of toys here on the desk, so if you want to see them, you need to get closer, otherwise it's okay. They will not show up there, that's just the screen. But we have a lot of live hardware, that's the whole idea, right? Usually we do this in classes, so we sit all around the tables and we play with wires and whatever, right? It's a little bit 2 levels. And with that, I think we are already live. And so let's start this. Thank you for joining us. I know it's the last one of the last day, yeah. My name is Cesare Garlati. I'm a founder of X5 Security, which is a young, small startup here in the Bay Area. But I think more interesting, I've been involved with RISC-V for a long, long time. Since the security group was 3 people calling each other on the phone. Hey, Bob, hey, John. What kind of video conference we use when we get the 3rd one, right? So, oh, let's try Zoom, that kind of things, okay? And I'm so glad to see where we are right now. 3 security groups, and it's fantastic. With me, I have Sandro. Sandro, why don't you introduce yourself?
Okay. So, hello, my name is Sandro. I'm a research scientist and invited professor back in Portugal at the University of Minho. I've been working all around security. I've been investing more than 7 years breaking trust zone. I'm now helping
yes, this is the place to say, yeah.
Try to bring this multi-zone approach, which I believe is a clean, simpler, and I hope better solution for building security.
And by the way, he's being kind of humble, but he's in fact in charge of a research team, very talented one, with many, many PhD students and graduate students. And most of the real heavy lifting that you'll see in what we have here has been done by Sandro and his team, okay? So thank you, Sandro, for joining us. Before we get into the details, just to clarify, okay? So X5 Security is a private company, is a startup, and we do have a commercial version of the things you'll see. But I've been a strong proponent of getting all of this framework. I propose this for adoption in one of the many, I don't know, being ratified in anywhere where it comes up, one of the groups, one of the specs. But I would really, really love to see this becoming part of RISC-V. And so there are typically 2 ways if you've ever been involved with standards. One is to go through standardization bodies and all the politics and big families and many years. The other thing is the de facto standard. Just put it out, getting the people to use it, and if it works, people will adopt it. And that's kind of route we took. You'll see real hardware, real customers, But as I say, totally involved with all the groups possible and happy to participate in the effort eventually, or to get any kind of contribution. And with that, do we have a clicker here? No, we don't have a clicker.
The mouse.
The clicker is the mouse. No, really bad. Okay. Okay, so we have structured this in 3 parts of 30 minutes each. So we will leave a little bit of 5 minutes, and we'll try to be on the 30 minutes, but we can change the agenda based on your interest. So the first part is really the 101 of RISC-V, not even security. So what I do to get something working, right? So what I do, what the hardware, we will see in a second. The second part is now that I have an MCU, which is in fact an FPGA running a bitstream, okay, what do I do to secure it? How do I put a trust execution environment? So security, in all of these conversations, security is really separation, okay? So how do I create separated environments that no matter what you do to them, they will keep staying in the boundaries the designer of the system has defined. Individually, each one of them can fail. That's the whole idea. But you will not be able to do lateral movement. People who have been in the business know the concept, mixed criticality systems. Something's less critical than something else. You get in from the weakest link in the chain, and then you do lateral movement. You pivot into what you're trying to do in your system, get control of the car through the CAN bus, getting in from the radio stereo. That's a kind of a simplification that happened in reality, right? So security in this case, how you keep things separated so that no matter what anyone does, stays into the boundary that you define for it, okay? You mentioned trust zone. That's the concept that trust zone developed more than 20 years ago now, okay? But you will see with some very interesting variations. And the last one is the multi-core. So MCU is good, it's great. What when I have multi-cores and I have Linux or any kind of AMP situation, multiple operating system running there. And with that, I think, Sandro, you want to describe a bit what we're going to do?
Yeah, sure. So we'll start with the basics, not the basics about security, but the basics about RISC-V. We will start by showing you how you can find a customizable RISC-V soft core that is available, and it was modified by X5 to implement other functionalities that were not available on the E300, available on GitHub as well.
Sandro knows me. I interrupt him all the time, and
Yeah,
he's
sure.
allowed to interrupt me all the time. That's our deal. How many in this room have seen this thing here? 1, 2, 3. We don't sell it. We don't make it, okay? And it's not going to be free, okay? So this is the standard FPGA. It's Xilinx. It's built on a Digiland board. I think there are 2 versions floating around. One is $120. The other one is 200 something. We work with any code we find out there. And the T100, which is a little bit bigger of the 2, basically runs all of them. So that's what you will see us using. When it says we get the bit stream, how many people are familiar with the concept of a bit stream? Okay, FPGAs? Good, that's a good start. Okay, very good. So we will use this FPGA, we will get the bit stream, modify it, get it to work, and there we have our RISC-V system.
So that's the first step in the chain. So we need a microcontroller. We will burn it on the board, and then we will point for a toolchain. When we have code, we need to run code on top of the microcontroller, so we need the GNU toolchain. We'll point also for the OpenOCD to flash the board, and we will...
That's where I interrupt you again.
Yeah.
Who knows what is this thing here? Yeah, there you go. So this is a head for JTAG, and the name is ARM something. That's the name of the part. So what we do, we use all open source, open standard. Everything is free. Nothing. It's all on GitHub. And basically, we use OpenOCD over JTAG to do GDB. OK? Did I miss anything there? No. OK. Who knows GDB? Who works with GDB? OK? So that's what we're going to do. OK? And that's the first part, right, of the 30 minutes. OK. And by the way, you will see in a second when I switch to the actual little thing. Eclipse. How many people work with Eclipse? That's OK. How many people work with other IDEs which is not Eclipse? OK. How many people go black screen of that? And dun, dun, dun. I do all of that. OK. How many people like proprietary IDE tools? Okay. How many people are forced to use proprietary IDE tools? OK. Very good. So let's get started. And so we switch to the real thing now. OK. OK. So how many people have seen this page? Because everything starts from here. OK. So what is RISC-V? That's the question. What is RISC-V? Is a processor? What is? It's a school project? That's what RISC-V is those 3 PDF documents. I'm serious. So RISC-V is an ISA. ISA is a contract in between the hardware and the software. Okay? That's how as of now, it's those 3 documents there. That's what RISC-V is. It's not a core. It's not a microarchitecture. The microarchitecture is not open source, not all of it. It's not freely available. The standard is. Okay? That's set the... Any questions?
No.
Anyone who disagrees, that's fine. Okay? So, okay, very good. So what we'll be using in this case is what's available right now, which is the unprivileged. And for security, you will see the privileged. These are PDF documents. That's what drives what we do. Where do I get Eclipse? Well, a good place to look for that is the Eclipse Foundation webpage. So in particular, what you need if you want to start playing with these kind of things is the CDT, which is the C developer tool something, T. But you also need to add a plugin. I would recommend you add a plugin, which is called the MCU plugin. Makes things a little bit, you can do without it, but makes things a little bit easier. So that's what you see here. So let's, don't get confused by the X5 Studio. It was just my attempt to see if I could change the name. And yes, I could, but it's totally 100% Eclipse. So there's no magic there. This is just my experiment there. We'll get back there in a second. Okay, so I have my Eclipse. So what I need to do now is to go and grab a bit stream. So this is one of the many repositories for X5. As I said, all of this is free to take. Go grab it, do what you want. In particular, one of the repos that you will find here is the FPGA one. There you go. Now, if you go and actually grab the end result, which is, I guess, here in the, there you go. So that's all you need, is this file here, okay? We're going to publish the PowerPoint. If you want a copy of the PowerPoint, I will give you my business card. Ask me. We have Kat, wave, hi Kat. So Kat is our business development lead, outbound lead. Any help, ask Kat, she can help you with that as well, okay? And so where is this bit stream coming for the FPGA? Well, it's coming from Rocket. Who knows what's Rocket? Yes. Go Bears, I'm a Berkeley graduate, okay? So you will see a little bit BS there, but I did business at Berkeley, so I cannot be held responsible for anything happening on the RISC-V side. So jokes apart. So the Rocket is what was developed. It's called RISC-V for a reason. It's the 5th iteration on that kind of exercise. The Rocket is the core. And so then on top of the core, you need some peripherals to make the SoC a little bit more functional. And so that's what is available. It's on some other repositories. You look around. So what we did was actually to slightly adapt the shell, it's called the FPGA shell, to use the Ethernet port. So we did it because it wasn't there, okay? So when we needed to do something real, so you will see an IoT device that connects securely on the internet, we needed to use the Ethernet port. And so if you want to use this one, use this one. Even for production, if you want to. It's completely free. Otherwise, you need to go to the source and add and change what you want, okay? Stop me anytime if I forget anything, okay? Now that I got the file, oh, by the way, who knows what is chisel? Is the best ID in the world? No. Okay, so chisel is what has been used at Berkeley as a definition language. I don't have a better description for the Rocket itself. But it generates RTL, so if you want to go the hard way with RTL, you go the hard way. Mixed opinions about anything, so I don't have a personal one about this one. But if you want to change this, you go with Chisel, and Chisel is a high-level description language for the hardware. It's based on Scala. It's written in Scala. Who knows what Scala? Okay? So I know what is Java, and I know Scala is not Java because I feel like I cannot do anything with Scala. But supposedly, it's a variation on Java. Okay. Let's do it. Sandro, you want to do it?
No,
I do it?
I can help.
No, let's do it together. Let's blow this board together. So we need a small wire here. Yeah. Now, there are two ways of doing what I'm doing right now. The hard way is using the tool provided by the vendor, which in this case is Xilinx. Yeah. And it's called
Viva.
Yep. And that's what we are going to use the first time. Vivado. Who worked with Vivado before? Anyone in the room? Okay. So here is the tough question for you guys. How big is Vivado? It's bigger. It's bigger. Try to run it in a virtual machine. Good thing, now we have Vivado Lab, which is smaller. How small? This small, 4 gigabytes, okay? But hey, it works, and that's what we are going to use. It's free. But then I'll show you how I do it. Forget about Vivado, but that's in a second. Okay. Okay. So now, if I remember it right, so open Hardware Manager. Okay. Now I need to click this thing here. Okay. It's there. Then I need to pick one of these guys. I don't necessarily, I think it's this one, right, Sandro? And then, don't ask me. I'm not responsible for all this. I'm just doing what needs to be done, okay? Which is add configuration memory device. I have no idea which one is this one. Which one is this one? Okay, gosh. Okay, now I think I put this somewhere here. Okay. Do you want to program? Yes, absolutely. Okay, so this is the file that I just pointed to you, the MCS, the bit stream, which is a small one in the end, so it's quite easy. I just downloaded it from GitHub, and I put it here. X300 MCS. Okay? Okay. Brr, working. It doesn't take long, just 10, 15 seconds, 20 seconds, something like that. It works most of the time. If it doesn't, it's because you just bought a new board and I changed the flash. So little sharing my experience. Same SQ, same boards. They look exactly the same, but they have different flash on board. And obviously, the driver will not work. So you need to really figure out what board you have in your hands, okay? But except for that, it works. Things on stage looks always lower than where they are when you are doing that yourself. Now I realize that. It's a good 40 seconds here. Okay, we did it. Good. So I press the reset, or I power the device again. Something is blinking here, okay? So I think it's a good sign that something is working. We'll see in a minute what's working. But okay, now this is the hard way, the way I see it. So the easy way is what I did. I'm sharing all of this with you, no problem. So, okay? So for each one of the targets that I work with, and I work with many, I created a little bit of a script. I think it's called a macro in the terminology here. But basically, when I want to do the same, I do something like this. Okay, if I want to do the X300 is this bit stream. That's what I can. No, that's all I do. And so I can change the image all the time. There's not much fun looking at the log there. But the concept is that you don't have to go through the UI and do all of the settings and save a project. If you go through many of these things, you just write the script, you run it. It does exactly the same thing. I find it better, okay? Very good. So let's recap where we are right now. We went online on a public repository. We got the blueprint of our hardware, of our SoC, not just the core. There are peripherals, there are UART, and everything else you'll see. We modified it a bit eventually. That's what we did. We have the Ethernet port attached to it. By the way, we did many other things. It's not just, I have a slide for that. Then I get this bit stream in the form of few megabytes of a file. And through two options of different ways, I burn my FPGA. How many times can I burn the FPGA? All the time, okay? So I blew a few boards, not because of that, but because the USB connector is a little bit delicate. And if you put it in the bag with the wire attached, it pops up, okay? Sharing all of my experience with you. Very good. So you see, it's ready. What you get if you play a bit with this kind of things, we have a slide for that.
Excellent.
Sandro, do you want to explain what this thing we changed? It's all for you. You can do the same. You can do more, less.
Yeah, the main modification was the inclusion of the Ethernet port because we are targeting to develop a secure IoT stack that we will see in a moment. But we also modified little things, like we boost a little bit the frequency because we had to process some cryptography. We will include Wolf SSL, TCP IP stack, FreeRTOS, everything in these small MCUs. So we tried to boost a little bit the performance. We also include more hardware breakpoints for debugging. It's a little bit better in that sense.
How many hardware breakpoints there are in the standard rocket? No one ever? 4. Is 4? Not enough, let me put it this way. If you start debugging and really doing things, you know what's a hardware breakpoint rather than okay, right? So if you have the code that's running in Flash, you cannot put the break, so you have to use something that triggers an exception in the processor. It makes the developer life easier. So that's something that we added.
Yeah, we still modify the configuration of the cache to increase performance. We realized in terms of development of the multi-zone architecture, since we were using 4 zones, we had like a one-way cache. So we modified to a 4-way set associative cache, and it boosts significantly the performance of our system. So
which took me a number of months to figure it out. So let me share my experience with you again, okay? So when you are in MCU kind of situation, system designer assumes there is one thread going, which is fair, okay? And so the cache basically fills up the instruction cache with something that is always in that hotspot. Now, if you start doing what we do for security, which is to break things apart, at all the effect, you have multiple hardware threads. They are not really hardware threads, but to the system, they are. And so what happens is that if you don't have enough ways in the cache, basically it keeps refreshing all the time, which kills the system, okay? And so why we put 4, well, I don't know, it's entirely up to the designer. Again, you can change this anytime you want. That's the beauty of this kind of approach. So 4 seems to be a reasonable number we have a demo here that runs 4 zones, but it's a little bit different approach than the traditional MCU, one thread, and just one of whatever, okay? It gets a little bit more towards a multi-thread kind of operating system and environment. And what else we did there?
We extend a little bit the memory available.
Yeah, more memory.
And more performance counters. And if you know RISC-V pretty well, you will know that the Rocket just implements the PILIC, the platform interrupt controller. We will also include some interrupts for the core local interrupt controller, the so-called
I ask questions all the time, to keep you awake. How many controllers exist in RISC-V? Controller standards, definitions and system, whatever you want to call them. Someone said 0? In 111, in one of the documents there are specs for the PILIC, as far as specs, okay? So I think 1 is, who said 2? Who said someone came up with the CLINT? Okay, the answer is 3. CILIC 2. Okay, now all of these things are PILIC, platform level interrupt controller. I get lost myself. CLINT, core local interrupt controller. And I give up on the other one. So that's one of the areas where we have very good people putting a lot of effort trying to standardize the bit. And I'm taking the opportunity to share a bit of my experience, right? So you will realize working with RISC-V that being an ISA, anything that happens, that's the way I describe it. Everything that happens inside the core, that's good because you define it. Anything that happens outside the core, that's platform. And so kind of gets kicked out of the specs and say someone will figure it out, right? I'm a little bit kind of provocative, but I can give you an example, right? So in the first specs, you need a timer in the core, obviously. And so in the specs, there is a couple of instructions, mtime and time CMP that sets the trigger on the timer. Right? Instructions. So you would expect to run them. It's in the specs and get something. Unfortunately, you will just get exceptions. Because turns out, it's not that people are stupid, it's complex, right? Turns out that if you have a timer, you want to have in a different power domain. So that when you go low power with the core, your timer, real-time clock keeps going, right? How you do the magic, right? So you do by taking it out. And so now if you use instruction, it's not going to work. So you need to go to memory mapped peripherals. But when you get into the memory mapped, it's memory mapped. So any implementation has different place and perhaps different granularity and different behavior and so forth, okay? So again, I'm sharing my experience. Feel free to ask questions if it's not related to this very specific slide. Okay, where are we? No, let's wait 1 second here. Yeah. What's next, Sandro?
Is the OpenOCD
OpenOCD and all of these good things.
and the two
Okay.
chain.
Okay. So, do we want to do next step and so? Okay. So, I want to show you something that actually works. So let's move to the second one, even if we have 5 minutes. Do you want to take a break? No. Okay. So let's move on with the next one, and then start actually building stuff and working with it. I'll let you, Sandro, introduce the next one. There you go. So what are we going to go in the next 30 minutes?
Okay, so in the next 30 minutes, we'll start introducing the trust execution environment itself, but focus on single core MCUs. Okay, we have burned the microcontroller. This is a single core implementation, MCU, and we'll start showing you how you can basically implement several zones, worlds, or domains. Pick the name you prefer. And these zones are completely separated from each other. Okay, you think in terms of a system or a IoT stack that you have typically, for example, FreeRTOS, for instance. You have FreeRTOS and you have the TCP/IP stack monolithically integrated with the kernel. This is why past October, not this one, last year, several researchers find 15 vulnerabilities on FreeRTOS. It was not on the kernel of the FreeRTOS itself. It was on the implementation of the TCP/IP stack. But since the TCP/IP stack was monolithic, a monolithic piece with the kernel, they were able to bring down the system. Okay. So what we are showing.
Question for the audience. What is the TCP/IP stack in Linux? Who said in the kernel? Yes. Yes. The kernel runs in kernel mode, which is high privilege. Anything that goes wrong with the TCP/IP stack immediately reflects into it. Unfortunately, the TCP/IP stack is the part exposed to remote attack by definition, because that's what connects the system. And so you will see in a second, we have a couple of slides. That's the actual application that we're going to build. It's a stupid one that moves the robotic arm and blinks LEDs, but we do this by keeping these pieces separated, okay? And I think we have slides for that, right?
Yeah.
Yeah, okay. That's the slides, and then let's do the actual. Okay, so already built up.
Yeah.
So how you create separation with RISC-V? It's not really different than how you do with other platforms, okay? So these are the very basic building blocks. And so what you see on the left side, I try to recap them. Obviously, there are many, many intense pages of specs behind all of this. Not necessarily absolutely well written, and everyone is welcome to make them a little bit more understandable. It's not anyone's fault, it's just really complex. So the two building blocks are, one, the privilege levels, or the rings, or whatever you want to call them. How many we have in RISC-V? Who said 4? Yes, we have 4 levels of privilege. Why? Because we allocated 2 bits. That's that simple. No. In fact, of the 4 privilege levels, the hypervisor level, which is H, is still under definition, as many other pieces, as I said. Okay, so what is the level that is always there in every single RISC-V core? Machine mode, yes. M mode, that's the highest level of privilege. If there's no M mode, there's no RISC-V core. It's that simple, right? What is the opposite spectrum? What is the most protected or unprivileged mode? U, for user mode. Do I always have U? No, not necessarily. It depends. In fact, when you boot the core, you will see a string that comes up, which is the extensions for the core. And if you see a U, you have the U mode. You don't see the U, you don't have the U mode. Now, if you only have M, there's nothing to secure. End of the story. Whoever did that silicon is not for secure applications. If you have U and you have M, then you can start doing interesting things, and that's all you will see. S is for supervisor. Supervisor is what mode, level, privilege, is what drives the MMU. So if you have a Linux-capable system, you have an MMU, hopefully, and then you have S that drives it. So I think I recapped that on the left side. But these are kind of scenarios. many, many questions from customer and prospects all the time, but what if I have S and M? So it's that simple. There are really three situations. One, you only have M. That's not securable, end of the story, let's move on, okay? Now we have M and U, which is a secure microcontroller account situation. That's very good. You can do really very good stuff here, okay? Now if you have M, S, and U, you have a Linux-capable system. You can do the very same good stuff in addition on having Linux. Any other variations on the team? I think there are people who want to do the S mode, PMP, these kind of things. I honestly haven't seen them happening yet, but any other mix is probably possible. I don't necessarily see this happening. Okay, you have the privilege modes. So some instructions work in depending on what state you are in the process, or some don't. In reality, if the same instruction is what CSRs, control status register, you can access or not. Same story as other platforms, okay? On the right side is the complement to it, okay? It's called physical memory protection. In other platforms, this is called MPU, memory protection unit. What it is no magic. It's a bunch of registers in the core, outside the core, memory mapped, okay? Where you can put some ranges of memory. So it starts here, ends there. And some policy, read, write, execute. And then if the next fetch of instruction or access to the data, whatever is the situation, right, happens in one of the ranges, good. If it doesn't, one of the 3, 4 exceptions gets raised, depending on what you're doing, and stops the core, raises an exception. Those are non-maskable, so synchronous but non-maskable, and so on. That's the basic, that's the story, okay? There's no other magic here. Now, this gets very, very complex, but if you get the concept, the processor the core at any time is in one of those states, and depending on what state or privilege you are, you can eventually set this kind of physical memory protection policies. You can change them as long as you want. Probably not really a good idea, but it depends what you're trying to do, okay? But the concept that these are not fixed unless you want them to be fixed. And I don't have the time, unfortunately, to go through all the details, but there is in particular one bit here. It's only one bit in the PMP configuration, which is called the lock bit. The lock bit prevents the highest level of privilege itself from changing it, and then submit the highest level of privilege to the very same limitation, which sounds so totally stupid, right? So why I would want to protect from myself? There is a very good reason, multi-core. You may have one core that boots the other ones, establishes, sets up the policies for the other cores, then locks down a bit, and let that core go with the highest level of privilege. Anything bad can happen there. We'll never be able to change the policy, so we'll never be able to affect the rest of the system. This is the end of the presentation. You will see one of these cores, multi-cores, doing exactly that. Any questions so far? Okay, I see you are still awake. And that's not fine. All of them checking email. That's good. Okay, what is NAPOT? Without looking at the slide. Gotcha, without looking at the slide. What is naturally aligned power of 2? Okay, let me ask you a different question. Let's say you have a 32-bit word with 32-bit registers, and you want to store the start address of your range. It can be anywhere in memory. How many bits you need? Well, 32. Okay. Now, I have a range, so I also have a size starting from that base, and that size can be as much memory as you have. That's another 32 bits. So here is my question. How do you put 2 pieces of information that are 32-bit each in one single 32-bit word? The answer is NAPOT. And I see people don't understand. It's really hard to deal with this stuff. But that's exactly how it works. If you assume some conditions, and you assume that your start address is in fact a multiple of the size, you can waste 1 0 to put in that address that separates what is the address, start address, from in fact what is the size. Don't feel bad if you're totally lost, because that's what happens. So Brandon Lewis, who knows Brandon Lewis? Chief editor of Embedded? Okay, so he wrote a wonderful piece, you can read it. And basically, at the end, he works with DevOps. Right? He comes out and says, all the systems have these kind of mechanisms, but in the end, no one uses them because they're too complex. It's that simple, right? And that's just the NAPOT, so I'm not going to test you with the other variations on the team. By the way, other architectures are even worse.
Much worse.
Other architectures have volumes and volumes of MPUs. They cannot even do what this is doing. That's not fun. OK, so if you understand this, I think you get 80% of the story about keeping separation or maintaining security inside the RISC-V core. OK, Sandro, why don't you explain what you're going to build? So we want to spend time on a slide so you understand the concept, right? But we are going to do this for you in a second.
Yeah, let's see.
This is the guy. Yeah.
Not going full screen.
It's OK. You don't need full screen there.
OK. Yeah. Leave it. So what we have here is basically the reference application for the secure IoT stack, what I was talking about. So we take this approach. Basically, when you want to connect an embedded device to the internet, you need some sort of piece of software. What we have here is in one zone, of course, we are running FreeRTOS, not because we love FreeRTOS, but it seems that people,
I love FreeRTOS.
It's interested in FreeRTOS a lot of, it's really famous. This is why Amazon acquired FreeRTOS. So we have FreeRTOS, we have the TCP IP stack because we want to connect this device to the internet, okay? But the key point here is that if you look at this, you will see two different zones. So FreeRTOS is running in one zone, zone 1, and the part that is connected to the internet, because it's the attack surface is what is exposed to the internet, it's blocked or in a cage in a different zone, okay? And we have also added other pieces like a root of trust where we use the WOF SSL. We have in another zone a small dumb terminal that we can exercise the functionalities of the system. But basically, the key point here is we have all the pieces that we need for the secure IoT stack to connect the device to the internet. Typically, they are mixed all together in the same memory space with the same higher privilege of execution. We take a different approach. We use this multi-zone secure nano kernel that is the underlying TE that provides the separation among all of these zones, and then we put all of these pieces or applications on top of multi-zone completely isolated from each other. If you want to add something
much
more.
to add. So typically the question I get at this point, so is this kind of security hardware or it's software? And my answer is both, right? Because you need a piece of software, is the yellowish stuff, to actually drive all of these hardware building blocks that I showed you in the previous slide. But the good news is that those hardware blocks are already built into the specs. They're already in your course. You have them. So it's just that if you try to make them work, it's going to be a lot of troubles. If you get something that is designed easily, you will see in a second, to make them work, it's more secure because in the end it works. Any questions so far? OK, now let me ask you a question. How big you think is the attack surface in the end, the only one that you need to trust, the yellow thing that works at the highest level of privilege? How big can it be? How many gigabytes? Well, that would not be good, right? So how many megabytes? How many hundreds of kilobytes? How many tens of kilobytes? Who says 1.6 kilobyte? Yes, that's the right answer. It's 1.6 kilobytes. When was the last time you heard something measured in 1.6 kilobytes, right? So it's ridiculous, right? So that's why it's secure. That's why it's safe. So this is not smarter or whatever. It's just smaller. And then you can knock yourself out and put all the hypervisors and whatever you want there. We run Linux on top of it. That's fine. But the whole idea is that what maintains the separation has to be so small that you can formally verify it. And there's no conversation about being secure or working or not. It's so small, there's no escape from that. Now, yeah, here is the question.
What are the benefits of a separation scheme like this versus SCL4?
Yeah, so there are many ways to create separation inside the system. And I don't want to point necessarily to one particular approach versus the other. Generally speaking, system-level software that is written in C, which is all of it, tends to have, first of all, dependencies from C itself, the C compiler, the C libraries, and the C runtime. Okay? There's no C here. This is written completely in assembly. See, color of my hair? The few left. It's really tough, but that's the way you do this thing. So that's the major difference. To get this level of, in my word, is security. You can replace and say of size. To me, it's the same. To get this level of size, you have to do it in assembly, completely in assembly. That's a major difference. There are many others. This is a kind of new way of looking at separation, which is lightweight. Even the underlying hardware, the only requirement I have is those few PMP registers here. It's the black stuff that you see there, it's the PMP. If you want to run an hypervisor, you need to have hardware support for virtualization. And switching context, it's level of complexity just. This is not to say that this, in fact, I think all of these are complementary. So security is a spectrum, okay? It goes from the way you do the microarchitecture, the way you deal with caches inside the hardware, the way you get up there at the communication level, operating system, application, user interface, it's all full. This thing does one little piece of the whole chip, but it does it very well because you can trust it. So that's my answer to you. So it's the size which translates in resiliency or attack surface. So people in security know less is more. That's the end of the story. The more security stuff you put, the less security you get. I cannot run that slide. I had it yesterday in another presentation. But OK. Question for the audience. Okay. How many lines of code are in the Linux kernel, vanilla, 4.x? OK. More or less than 100,000. More. More or less than 1 million. What? Who says more than 10 million lines of code? More. Who says 17 millions and a half? Right answer. You missed my presentation yesterday if you know the answer, but there is a nice website. It's online. You just point the URL to any code you have and just gives you for all the, just parsing, figures out. So we run Linux. We love Linux. I'm a big supporter of open source. 17 million lines of code. Keep that in this part of your brain. Now, the other part of the brain. We have software experts here, so everyone went to EE CS programs. What is standard ratio lines of code defect? So how many defects per lines of code? One defect every time you write a line of code? That's really bad coding, right? So 10 lines of code for a defect? One defect every 100 lines of code? So Google, the best I could find is what's been used for the shuttle program, which is the most complex machine ever built by humankind. Okay? One defect every 10,000 lines of code. I think that's the world record of whatever, right? And all the money that goes into it. Okay, that's the other half of your brain. Now put them together. 17 million lines of code, 10 a la minus 4. How many accidents are waiting in the kernel? 1,700. That's just pure math. I don't even know if you can talk about lines of code when you get to 1.6 kilobytes, but it's definitely at 0.000 whatever you want to put there, okay? That's the end of the story. Okay, I think we touched upon all of this. Time to do something for Rio.
Yeah.
You want me to do? You want to do? No. Okay.
It's your machine.
Okay, so now I'm going to go and get all of this, which is, again, all open source or free to get. And in this case,
Not this one.
no, this one, but not this one. Okay, and so this is the multi-zone SDK. Again, the standard itself is completely open source permissive. It's actually one of these repositories, multi-zone API, there you go. And the multi-zone API is ISC. ISC says, do whatever you want, don't go back to Cesare and complain, okay? That's the policy. No, I'm serious, that's what he says. Where you can actually read it. Do anything with your code, and there's something more somewhere there. ISC license. ISC license. Is it permissive? There you go. This is the license. As is, don't complain with Cesare. Can you read Cesare there somewhere? But do whatever you want. Sell it, use it. Don't tell people to knock yourself out, okay? Okay, so let's go grab not the standard, but the implementation. And so this is the multi-zone SDK. Here we go. Okay.
So let me just add something. We showed the multi-zone secure IoT stack, but of course here, for the sake of the time, we will present a minimalistic version or a minimalistic view of that implementation. It's a much smaller demo, not much, but in terms of functionality, it doesn't run FreeRTOS, that is per se a real-time operating system. It's 3 bare metal applications running completely isolated from each other and using the secure communication.
Yep, so it's all real, it's all there. So these are the ones you saw in the slide, 4 zones, and it includes, I'm just pointing at the repo, right? So we have FreeRTOS, the Pico TCP, which is that open source GPL, full-blown TCP/IP stack, and a multi-zone. All of this is GPL. Some of that is licensed for commercial use, but this will be a little bit too much for the next, gosh, time is flying, few minutes. So we do something a little bit more digestible, which is the simplified version. It's 3 zones instead of 4, basically. That's what it is. Multi-zone SDK. Okay, so what it looks like, we can look here, or I think it's better, more elegant if you look somewhere here. So what it looks like to build a project that includes security, right? Well, first of all, you need to break it in pieces, all right? I think that's the most disruptive kind of thing mentally, because so we've not been trained in school to build things in pieces, right? So you do something, a lot of code, a lot of libraries, different compilers, and the linker sucks everything up, boom, there it is, just put it somewhere, it works. Yes, but it's one thing, that's the problem, right? So here's what we do. We do same kind of thing. Every zone that you saw in that block is just C code, really, nothing dramatically different, but you have 3 of them. And each of them has its own executable, right? So stop me if it's not clear what I'm saying, but once you break your system in pieces, you don't assume anything on anything else. Some pieces might not be there at all. Some pieces might be designed just to exploit vulnerabilities. That's called malware, right? It doesn't matter. You don't have to put them together. This system pulls them together, but it does according to the policies. And that's you'll see in a second, okay? But that's what it looks like. These are the zones that we are going to deal with. It's plain C code. All of this is new. In particular, this is the new lib. Who knows what's the new lib? Okay? New lib is a smaller version of the C-lib. It's still big, by the way, okay? So if you put a printf there, it gets up to 20-something kilobytes, okay? But it's okay. That's the optimized one. In the second zone, we have something that just blinks an LED. Here is what, and you press some buttons, create some interrupts. So this is fully working, okay? But here's what the main looks like. It's just a loop. I'm just trying to convey as much information as possible, right? So, but generally speaking, what these executable, these zones are just loops. Who works with Android? No one works with Android? Okay. So Android embedded this concept in the looper. There's a class called looper. It's just something that loops and does something and then does nothing. And that's how embedded system really works. Wait for something to happen. In this case, we also send and receive messages, but wait 1 second for that. And I think the third zone is the one that moves the robotic arm, right? So it's the most complicated one. And what it does is another of these loops. You see, while one. And if I press some buttons, the robotic arm does some things. And in the end, I send and receive messages, and it goes back. This is really the key aspect of all of this, right? It's like you have multiple cores, multiple threads. So once you are done with your stuff, you want to move over. and that's typically in programming language in operating system is called the yield. This is the cooperative aspect of the system. All the zones behave, they are well written, there are no bugs, no out of memories, no nothing, perfect magic. And when it's time, they say, hey, you, next zone, go on with your work. That's ideal. You cannot rely on anything safety critical, on anything like this. And so what, in addition, we propose is the preemptive scheduler, which is built in, you will see in a second, where you can set up a tick time. The tick time tells the kernel, the yellow stuff that you see there, when it's time to move on, regardless from what the zone wants to do. And I'm going to show you, we are going to tweak a zone, put just a loop, stupid loop that does nothing. You'll see that everything else works just fine. Just that zone is stuck. That's the concept of safety. So as you can see, security goes way beyond physical memory protection registers. Okay? It's all of these kind of things together. Are you still following me? Okay, I know it's getting late. Okay, so someone, not necessarily who's responsible for flashing ultimate architect of the system, produces pieces. In fact, they can come from different vendors. That's good, because you need to trust them. Zero trust, that's the model. I don't care. You'll see in a second. I put all of these things in cages, and they cannot escape the cage. They behave badly, too bad for them, but the rest of the system is not affected, okay? In fact, you can deliver and drop these binaries at any time throughout the supply chain, which is the other holy grail, right? So I don't want to put this at a fab or wherever it's this, at Foxconn. I want to put this when the device is in the end of the customer, so they don't have to, first thing they do, wait for 2 hours for the next update or whatever. Right? So that's a bad idea. That's a kind of a model, new model that this opens up. So zero trust and all throughout the supply chain in the hands of the end user of the device. Okay, so let's look at the BSP. How many people are familiar with BSPs? What is a BSP? Board Support Package. It's a trick to get the same code work on different hardware. And that trick is just to have multiple directories, and you point to the right one. That's what it boils down to be. So we support many hardware, as you can see there, but let's pick at this one, and let's look at what's interesting here. There you go. So let me shock you, okay? Yes, you're going to be shocked. That's the whole exposure to security you will ever get dealing with this kind of model. So let me repeat, the multi-zone approach to secure, which is open source and hopefully standardized in this file, is this. There are no files to compile. There's no source code to mess up. I saw some other presentation or other security or separation thing that says, and make sure there are no out of buffers. What? What? Is that a security system? Make sure that's a security system. You write in English your policies. This is not the top of the file. This is the file. This is as real as it gets. What it is a bunch of region attributes. Those PMP entries, okay? So start address, end address, or sites. With a policy, read, write, execute. Can I write here? Can I read and write? Whatever. You can have as many as you want. That's a question I get all the time. How many zones are needed in a system? What's the right answer? It depends. It depends what you're trying to do with the system. I just show you 4, but if you're trying to do 256 zones, you're probably trying to replicate the behavior of a multitasking operating system, which is possible, but it's not probably the good idea here. At this level, you want to map pieces of your hardware to each zone. And so typically, trust zone, who knows what trust zone is? Of course. Trust zone. How many zones you can have with trust zone? As many as you want, as long as there are 2, yes. Which is really 1, because you cut in 2. So here you can have as many as you want, for real. And you can change them anytime you want to, just to refresh the device, okay? I'm not going to go through the old details, but for whoever has been exposed to the trauma of reading those hundreds of pages of MPUs, memory protection units, and not figuring out anything, and I'm still there, Sandro, where are you with your MPUs, man? Or Trazon, even worse, okay? That's all the complexity you need to know, which is if you know where you put your stuff, these are the cages, these are the boundaries, right? See it? Pay attention to something very important there. We are mapping also peripherals. One zone controls the robotic arm. It needs to access the GPIO line to move the robotic arm. That's where the GPIO is assigned. These are all memory mapped resources, so you're not just assigning memory. This is not a memory protection schema. This is how you cut out all of your SoC, all of your hardware, multi-core, and assign pieces to whatever needs to access them on a need-to-know basis, okay? If you don't get that piece of hardware, that code will never be able to do anything. Okay, I think it generates a lot of exceptions. The tick time expires, and the world is over, okay? That's a kind of basic concept. There's a final thing that you want to point out there, interrupts. You can also map interrupts to those domains. We call them zones, call them whatever you want, containers, whatever, right? So why interrupts are important? Because the big flaw of most of these systems, including some of the slides I saw in previous days, is that it's a beautiful model of separating things, but then you need to run hardware, real hardware. And real hardware need real drivers. And real drivers, I'm provoking some question there. Yes? Which one in particular? Any line, okay.
We'll highlight one.
Thank you.
Pick this one.
Okay, so would that be a good line, the first one? Okay, so we are looking here is based on the design that the schema I presented to you. This is one of the zones. It's zone number 1. It's one of your domains. And so this domain has been assigned through these policies a number of resources or pieces of your hardware. The first line tells one of these pieces that are allocated, associated for the exclusive use of this zone, and in fact is a piece of memory mapped whatever. In this case is memory. It starts from the address 20401000, and you get 24 kilobytes. I have no idea what it adapts to. You figure it out. And the policy assigned for zone 1 to access this piece of memory is read and execute. And so the comment that you see after the hash, it's a comment, says, this is my flash. So in this specific case, we are running out of flash, zone 1, and so the attribute that we need is read and execute. Make sense? Yeah. The second line below is the same, different address, different size, but says read and write. Well, that's the RAM. More precisely, the first part is for the text segment of your program. The second part is for the data segment. Multi-zone doesn't need to know, doesn't care. So you give addresses, starts here and there, and the policy. Here, and now I ask the question. So why I need read and execute for my software, for my program in Flash? Wouldn't be execute enough? It's a fetch. I just fetch instructions, right? So why there is a read? Who's saying because the read-only segment is in fact by the compiler put there? That's the right answer. So the read-only segment or section of your file is typically, that's where it goes, right? Unless you do some. So there are some pieces of program that are not executed, are read by the system, which is not the data. Okay.
How do you protect between two different programs? Because right now I see that RAM has access in all these zones, right? And if you have multiple things that are running, multiple tasks that are running,
right?
Can I protect between these tasks?
I'm not sure I get the question, but let me try. So the comment says RAM, but the addresses are different. So these are different pieces of RAM. Is that a question?
Can I just try to add something to
Capacity
get straight to the point? The key point here is that in each point in time, you will have just one zone running because we are in a single core MCU. And since you have these policies are enforced for that zone in that specific point in time. If you change the zone, you dynamically change the configuration so that the next one get the next configurations and cannot access the resource of the other ones. That's basically the key point.
And I'm not sure that was the question either, but try again. No, try again. What was the question?
No, that answers.
Yeah,
you got
because
it.
you have different segments of RAM, but in each point in time, that zone that is running just has access to that specific resource.
So technically, it's called temporal separation. That is the basic of any kind of time slicing kind of operating system. The tweak here is that this happens in sync with those hardware mechanisms. So at any point in time, one of the zones is in scope, okay, is executing, and so the whole system is configured so that that zone can only access and see what is assigned to that zone. Let's make a little bit, okay? So those PMPs are dynamically assigned. So you can change that, and that's what the nanokernel does, among many other things. Okay, I think time check. We are doing good. How much time we have?
30 minutes.
30
minutes.
30 minutes, so it's time to get things going. Okay, but this is really what needs to be understood. So let's build this system here. Okay, how many people want to build this with Eclipse? Raise your hand. Okay, no one likes Eclipse. How many do want this from the command line with a let's, people don't like, okay. I just press the button here, it works. Anyway, okay, you want this to do the hard way. Okay, so where is multi-zone SDK? Here it is. And open a terminal, set the environment. 1.
Don't forget to put the cable.
Yeah, thank you, Sandro. Make, GCC, okay, done. Done. Let me check if I have a buffer overflow condition in my 35,000 files I have to link to the kernel. Oh, what is the optimization? Minus 02, minus 03 to me. What's the version of the library that goes, done. You write that file, it works. Did I show you the nanokernel code? No. You get to see it if you want to, but you don't. You don't need it. Yes?
So what happens if you do have a mistake in the configuration you do between zones?
Yeah.
Would it be picked up in this code?
Absolutely, and I can actually show you right now if you want to. The question is what happens if you get the configuration wrong, okay? Defining what wrong is, it really depends, but generally speaking, the system will give you a warning if you are overlapping any resource, because that's probably not a good idea, but sometimes you have to do it, and that's exactly what's happening here right now. So that warning that you see says that zone 3 is sharing something with zone 2. Did I read it right? Yeah. So why don't we go and check? That's exactly what happens, right? So let's go and, sharing is possible. You can overlap, right? It depends what you're trying to do. And to be more specific, if you're doing a split buffer for high-speed transfer, that's typically what you want to do. But let's start from the beginning, okay? Let's bring up the very file so that we check what is being overlapped, okay? Okay, so zone 3, range 4. 1, 2, 3, 4. Oh, GPIO. Here is what's being overlapped, okay? So the GPIO, in this case, is shared by 2 zones. Why? Because one is blinking the LED, and the other one is moving the robotic arm. It's okay to share the GPIO in that case? Perhaps yes, perhaps not. It depends on the situation. But if you don't want to do that, which is more sensible for DMA controllers, these kind of things that have access to any kind of resource, you can have the driver, little bit of code, for that specific resource, the GPIO in this case, in one zone. You can have as many zones as you want, right? So you can put your hardware that you want to plan to share in one zone, so no other entity has access to that hardware except by going through messages. And that message will be validated, compared with the policies, and if you have access to those 2 lines of the GPIO, you'll get it, otherwise nothing happens. I know you're tired, I know this is a lot, but those are very good questions, okay? So let me repeat, nothing prevents stupid people from doing stupid things, but there is extensive checking here, and you get, if I read warning, and I say, oh, what? What? Okay. Different thing to say, figure out how many, I don't know, buffer overflows are possible. But good point, yes?
Can you define an exception as saying that's an allowed warning?
Absolutely. Hey, it's open source, you can do what you want. I mean, It's really up to the designer. No, I think the most relevant thing about this session is to note something that usually it's a question I get from the smart people. So I know I have smart people. If anyone wants to ask a question, this is the time to show up. Okay, so the question usually goes along these lines. How many zones can I have? As many as you want. How many resources I can assign to each individual zone? That's my question for you. How many things you think I can assign?
How many PMP entries you have on RISC-V course?
If you understand the way it works, and I'm going to shock you again, there's no limit if you follow this kind of framework. Because there are ways actually, without getting in the critical path, to actually smartly managing those entries so that you can have as many as you need, okay? We've been doing this for a long time, so we figure out things. But just to give you a sense, some core don't have MPUs. Those are not secure. Forget about that. Some have 4. You can still run a system with 4. That's the whole idea, right? 1 for the text segment, 1 for the data segment, and 2 for some peripherals, whatever, right? But if you need more and you only have 4, it works anyway, okay? And I see people intrigued and happy to have share a little bit more. Some of this is covered by some proprietary information, right? But the answer is, you're right, as many as the system gives you, unless you have other means, and we have other means, okay? But 8 is a good number. By the way, why not 16? Just put 16 all the time, right? Oh, come on. Anyway, so, okay, good. So let's do it. So we build a system. You saw the toolchain extension kicking in, reading those policies, and the output all of this is somewhere in my directory. Let's see. Very good. So for zone, can you just, please, let me use my thing here. It's so more convenient. Okay. So each zone now has generated its own executable. No surprise. That's the whole point of zero trust, right? I don't care. Whoever, come up with something. Even if it doesn't run, doesn't matter. They have their own executable. So zone 1 has 1. Zone 2 has 2. Zone 3 has 3, trust me. But then in the end, what we really care is this one. And this is the sum of all. So the toolchain extension, actually, you have a slide for that, right? So why don't we show the slide so that it's a little bit more visual. Sorry. And then we are going to put that in FPGA. You finally will see things happening, okay? Okay, so here is what happened. We have that configuration file. That toolchain extension, which is the little, you couldn't notice it's 200 milliseconds, but the warning that came up and whatever, is what picked all of these binaries. The policy file that you see there, injected at 2 kilobytes of nanokernel, which really we don't want to mess up with because that's what keeps the whole thing going, right? And generated a signed image that goes into Flash, which is what you see here. That's the X file that just pointed to. So let's play with the system now and do something meaningful here. Okay, so
Plug the cable to them.
Put the cable, okay. Yeah. Thank you for reminding me, otherwise it would not be fun, right? So put the cable. So the cable is that JTAG, OpenOCD over JTAG. I'm going to flash it so we can actually do something with it. I think we do this like this. Okay. My mouse. Okay. So we make. Now we load.
Not that one.
Not that one. Okay. This is the X300. Did I make it for the X300? I don't know.
Not sure.
Not sure. So, you know what? Let's do the thing. Make board equal X300. But, by the way, I wasn't making this up. It's 245 milliseconds. Okay? That's the time it takes to apply the policies, create the image, and sign it. This is not the compilation time. That's obviously dependent from the size of the file. And now load it. Okay. The first time we need to reset it, right?
No, but it's going.
What, you want to go it, wait, or I would reset it. No. Typically here is where it gets a long time. Whoa. That's the beauty. So my comment is the beauty of open source, right? Every time we get something out of the repo, it works slightly differently. And so sometimes it takes 1 minute for the first load. This time it took a few seconds. So, okay. But it's running, right? Very good. So let's remember those zones. Now I'm going to connect to this system from one of the zones. So I'm going to open terminal. I don't remember which port is this one.
USB2?
2?
I think so.
Ah,
Yeah.
it's working, yes. So let's recap where we are. I showed you how to build your own RISC-V core out of completely free repos and good stuff. How to put it on an FPGA. You have low-cost FPGA. FPGA is running. I show you how to use open source tools, all free, all open source, to compile, link. We could debug, but yes, we don't have time. And then finally, we flash the device. So we have a fully working system. I could ship it if I want. I could sell it if I wanted to. That does something, but does something in a secure way, meaning in a separated kind of isolated way. Let's see what it means. This is one of the zones. This is bare metal. Those are those main files that you saw there, really few lines of code, right? Nothing really dramatic here. Z1 stays for zone 1. And so what you see here is a bunch of information coming out of the core itself, okay? Who wants to tell me something about this? A for atomics. M for, okay. Those are the extensions available in the core, okay? And this is coming out of a register called MISA, machine ISA, yes. And so that's a CSR. That's a privileged one. Oh gosh. Did I tell you anything wrong here? How is it possible? I didn't touch the code. It's running in user mode. This is a privileged register. What's going on? What's going on is something that we added as part of that framework, which is complete wrap and emulation. So that you get your executables. We run FreeRTOS there. FreeRTOS doesn't know he's running in a cage. He's happy. He thinks he's no, God on earth. He's not. He's running in user mode. So anything goes wrong there, stays there. It cannot escape the cage, okay? So this is just an exemplification of what's happening there. All of these registers are privileged. But as long as you read only, and again, I guess that he's going to have a next question, which is, but can I change that configuration? Yes, you want to ask? Yes, you can change that configuration anyway. But it's a way to show you part of the solution, which is the old concept here is that the less you do, the less you can screw. That's security, right? Less is more. So don't touch your code. If you have code that is running today, just drop it here, and it works in a secure way. If you start touching things, then things can go wrong, right? OK, so let's do something a little bit more interesting. We hard-coded a number of sample commands just to exercise the separation and check that we are doing the right thing, OK? OK, PMP is something that reads those privileged registers for this zone. Remember, it has only access to his own world, right? And so here is the configuration of those entries. If I open the file and compare to it, you will see those values. 241,000, 241,000, 8,000, 1,000, and 1,003. Okay, so this is as real as it gets. Okay, cool. What do I do? Oh, let's try to break this system now. Let's try to hack. And so we coded something like load and store. RISC-V is called a load and store machine. The only thing it can do with memory is read and write. And so let's read something. Let's load something. And in fact, let's load something from one of the addresses that my zone has access to. And in this case, with very little fantasy, I pick the first one. What do you think will happen? It's in my range. The policy says read, I'm reading. Whew, it's working. And there is a 9.7 there. Who cares? Now, let's do something a little bit more different. Let's load, but from an address that is not in my range. This can be an overflow, whatever you can come up with in your zone that tries to get something out, okay? I'm looking for volunteers who want to propose an address that is not in those ranges. Let's see how fantasy you have now. So, okay, the number is?
0, 0, 0, 0, 0, 6, 6, 6.
Okay.
The number of the devil. Is that it? What do you think is going to happen?
We're going to summon Satan.
Oh, nothing is happening. You cannot do that. Sorry, you're trying to break a secure system. Too bad for you. Come back. When you get something more complex, with many more lines of code, and eventually you will find something that breaks. This one it cannot. So besides joking and keeping you alive, what you see here is something very interesting, I think. I get really excited by that because it's the hardware that stopped me. It's not any software layer. So the software defines, puts things in place, but it's out of the way. This is the core. You do if you look at the code, please check it out. It's on GitHub. There is really a load. It's hard-coded. It's inline assembly. It's a load, LD. You can, I wouldn't know how to break that, okay? I'm good at breaking things. I wouldn't know. Now, if the implementation is screwed, that's a totally different story. But at this level, there's nothing you can do, okay? Now, I want to point out something else. The exception actually comes up with 3 values. What are those 3 values? RISC-V people in the room. You don't read the specs. Why not? They're so interesting, right? Okay, so the 3 values that we embedded into the ISA are, the first one, well, is the code of the exception, which in the RISC-V jargon is called trap, but it's a synchronous exception, okay? And it's an X5. Aha, now you know where the name of the company is coming. That was the first exception we were able, no, seriously, to trigger, say, yes, it's working, it's real, okay? It's a true story. So the other 2 are the address that this instruction tried to load, and I guess that the 66, I cannot see, but it should be the 66 somewhere, right?
Yeah.
Is there a 66? Yeah. So, and the other one is the address of the instruction that tried to do the load. And that should be in the range of our first range, because that's our executable code. Okay, we don't have the time, but we could try different interesting things, such as, for instance, write in one of the ranges where I do have access, but I'm not allowed to. Or execute where I cannot execute, just the usual traditional hype spray. You throw instructions somewhere and you somehow get the processor to jump into it, and it starts as trampolines, and who knows what's a trampoline in this context? Okay, very good. Okay. Who knows what's a privilege escalation? Okay. Bad things that can happen to Linux kernel, basically, okay? Because there's nothing wrong. It's written in C. C is an unchecked, unstructured data type, unchecked data types. You can do any smart things and any bad things with C. Okay. I want to show you a little bit more action here. How much time we have more?
12 minutes.
12 minutes, gosh. Okay, so let's send and receive messages at this point, okay? Again, you break the system in pieces. It's separation, is not isolation. What's the difference? Is that you can still get the system working as a whole if you start sending and receiving messages without sharing anything, okay? There's nothing to share. So I'm going to send a message now, send, to my destinary, which is zone number, 2. And the message I'm going to send is whatever, a byte stream, whatever you want to send. In this case, I send something like ping. And zone 2, which is running, is there, replies. You see, it says Z2 and says Pong. That's, if you look at the code, that's how we coded the listener for messages. It can do anything. In a minute, I'm going to connect the board, show you this on Linux. I'm going to send a message that says, starts the robotic arm. And the robotic arm beep, starts and do nice things, okay? That's the very basic of the whole story, right? You define your security posture, you define those cages, but you leave a mean for the system in a secure way, because, again, it's in user mode to send and receive those messages that are really the replacement for API calls. So in a world where you have a shared memory, you have API calls. You put something on the stack, some parameters, this is the call, something comes back, return, and you go on, but then you share. Here there's nothing to share, you send a message, and eventually the zone replies to it. But all of this must be really heavy on the system, right? No, let's run some stats. Okay, so what stats do here, again, those are built in so that you can try yourself. It just exercises this context switching among zones and goes through a full round trip. In this case, it's 3 zones, whatever. I don't care how many microseconds, I couldn't care less, this depends on the hardware. But what's really important is what you see at the bottom of the screen, which is statistics measured in the kernel itself. And so here is the answer who asks how heavy it is. This is real numbers, it's not fake, right? So a full context switch with all the things I described, and in fact, there's much more that I cannot have time here. In this case, is 121 instructions. I see you're blown, right? Because you're already thinking. There are 32 registers in RISC-V. To do a context switch, at minimum, you have to save 32, read 32. That's 64 instructions. Oh, boy, there's a PMP registers and a bunch of other timers. And you do that in 120 instructions, yes? So other hypervisors, in their possible best implementations, which is not on RISC-V, it's on MIPS, will require at least 500 cycles. We're talking about almost orders of magnitude. If this is actually 32 bits, but things go a little bit slower. It works also on 64. On the 64, there's less stuff to do because obviously words are bigger. And so that goes even lower. Does it make sense what I'm saying? Okay. Sandro, do we want to get the robotic arm to move and do something more interesting? Okay.
The big one.
So let's move to multi-core. Why don't you present the slide and I play a little bit with the hardware here. And we finally get this nice toy here to move around.
This is the third part of the tutorial, where we basically show how we scale the system from these small MCUs to a more complex architecture. We have tried this one in the Polar Fire SoC. Basically, here we have the setup.
How many people know what's the Polar Fire SoC? Well, we're doing a good job. So we are partners of Microchip. Microchip acquired Microsemi. Microsemi is a founding member of the RISC-V Foundation. And so if you want to try, this is what you need. But you will not be able to buy one, okay? Because besides being extremely expensive, it's a small production, so you will not get one, okay? Don't worry, because you need something more. This is just the FPGA. You need also some core that does something and so on.
At the end of the day, the Polar Fire SoC will have everything embedded in a single chip that has basically...
I think this is $3,200 of hardware, okay, that you cannot buy anyway, okay? The good news is that all of this has been put together in one single hard core, actually 4 cores plus 1 hard core inside the FPGA. That's the Polar Fire FPGA, been announced a few days ago, generally available starting from the summer, and in volume by the end of the year. That's the first silicon, in volume production of silicon for a RISC-V core, okay? Anything else has been experiments, like this one, or internal implementation of other companies. So if you want to buy a RISC-V, anything in silicon, that's going to be the first one, okay? Unless someone comes in before, but that I know. So this is 1 gig. It's 5 cores, 4 plus 1. The 4 are on the right. It's Linux capable. We're going to run Linux here. So why don't you go on with the slide, explain a bit how it works, and I'm going to plug in all the wires.
So the idea here is we have this platform is a good fit for mixed criticality systems. And if you know, who inside this room know what is a mixed criticality system? So it's basically the trend nowadays in the industry is you need to consolidate more and more in a single platform to lower the so-called SWaP-C, size, weight, power, and cost. Okay, and the idea is to bring on the same SoC like Linux-capable cores plus small MCUs. So here what we have is we have 4 big cores, Linux-capable, that run Linux, but at the same time we want to provide some sort of determinism, real-time, or some secure environment on the small core. So what we have here is we run the multi-zone separation kernel on the small core that provides these isolated or separated zones. And we put also the big 4 cores in a big cage so that these cores, whatever happens on Linux, doesn't affect what is or need to be secure on the small ones.
Thank you, Sandro. We are at the end of our 90 minutes, so we're going to finally move the robotic arm that you've been waiting so long for. Just let me comment a bit on this line and perhaps get a couple of questions around this one, because if you really get this one, you got the whole thing, because there's nothing more complex than this. So any questions with regard to what? Yes?
What is the size limitation of IPC message?
Yes. What's the size limit for IPC messages? Infinite. It's a byte stream. There's no shared memory. Nothing is allocated. It depends how you cut them in chunks. And so those chunks are up to the, so we publish the specs. All open source, do what you want of them. Please help us make them better. Let me show you. The answer is, let me show you. If we go on our website, or it's GitHub? Our website? Okay, and then we go
download.
To Linux. Am I still online?
Doesn't look like.
I think I lost the internet. Yeah, I lost. Oh, because I plugged in the wire. Okay, so go on this website, check it out. We publish the specs. It's a PDF document, and you will see how it works, but there's no magic. It's a mechanism of exceptions in the course. Who knows what's the SBI? SBI. Yeah, so that's a kind of. So SBI is still work in the making. We are working hard on that. So in the meanwhile, we just came up with something very small that really works. Will become SBI or not. But that's kind of mechanism, okay? Very good. Any other question? By the way, messages are not intended to move data. Let me explain. So if you ask this because you want to move data with messages, that's not how you move data. The way you move data very, very efficiently is with DMA. DMA, one of the many DMA channels you have in any little piece of hardware these days. You set up your transfer, get off the way, the system does the magic. Even if you want to zero a block of memory, you do with DMA these days. It's way more efficient, okay? How big is the size of a DMA transfer? Infinite, okay? Yeah, it's because I connected my Ethernet port here. So let's go back to that one. Okay, so what we're going to do here, we are going to exercise. I'm going to show you now live. So the system is working, Linux is working. I'm going to show you in a second. What we're going to do is to connect to one of those zones. They are separated there, either through some dedicated hardware resources, the UART port, or through Linux. Because to Linux, all of this stuff here looks like a character-based device. So we have a device driver. You read and write to it, and the communication goes on. Anything bad happens here, and you have to assume everything bad will happen here, doesn't affect in any possible way what happens here. And that's ridiculous. So one of my critics to separating anything in any of these cores, we went through that, right? Two things. Highest level of privilege, which is this one yellow here. If your SBI is running there, you can do anything to that core. Not to the other cores, but to the core you can do anything. So your trust base becomes bigger immediately, way bigger, okay? So to share the same core, just because of that, which is sharing the highest level of privilege, not what keep a satellite, $2 billion of satellite up in the sky, okay? We'll not risk with that. But there is something more important, which is the cache, okay? And we are working at defining standards for managing caches. But the point is that if the cores share the same L1, L2, if something is in cache, something comes out of cache. That's the work of the cache. Gosh, that's a big flaw. What do I do? Well, I know what Microchip has done with the Polar Fire. This is for aerospace and defense. These are expensive components, but can be done. So what they have, and it's all public information, check their material. We've done webcasts about that. And I can point you to people who know more about this if you want to, but the whole idea is this one. Those caches are addressable, which sounds a little bit, you address the cache is transparent, right? Yes, it's transparent, but if you address it, then it gets locked. That line gets locked to the core that addresses it. And unless it releases it, it stays locked forever. And now you can speak with security with me, because then I'll start having a conversation. Say, okay, the cache is locked. Good. No one, the other cores can do anything bad. They will never access my stuff, okay? So people familiar with the whole idea of out of order and even branch prediction, anything that goes out of flow and gets stuff in cache is completely immune in this case. By the way, this is not out of order, so that you know what's out of order, right? Next year, okay? Next year. Okay, let's get this run.
1 minute.
So, 1 minute. Okay. In 1 minute, we are going to get the robot alive. Okay, now you know everything you need to know. So I'm going to open, well, let's open an SSH. Actually, let's ping the board. Okay, the board is live. As you can see, I'm going over Ethernet in this case, which is if you can do that, you can connect any system at this point, right? And so, okay, the password is hex5. And yes, I mean, yeah. So Linux is working. This is not faked. But that's not what I want to show you. Let's see what kind of devices I have. Aha! This system has a device driver for some hardware, which is in fact the other core. Cool. And in fact, you have one entity of this device driver per zone. Aha! You can write, read. It's just seamless integration with Linux. No new languages to learn. Languages on top of languages that create meta language so that you, this is working, okay? Let's see what you can do with it. Who knows what screen? Yeah, it's a console redirection. That's in the end what it is. So let's redirect to one of these devices and see what happens. 1. Aha, I think I know this guy. Here is what's happening, yes. So what you see here is one user mode application in Linux interacting with an enclave. Your enclave is out there, somewhere else, completely separated. There's no way to do anything here. Nothing is dynamically allocated. It's all static. It's all burned into your flash. You cannot beat that. It's enforced by the PMP. Unless you break the hardware, you cannot break this. So I'm not going to show you the commands because now you are familiar with that. So it's the same story. What I'm going to do is to do the same in the 30 seconds left. I open a second SSH session. The password is still hex5. This time, I do a screen. Aha, this is zone 2. And now let's see what happens here. This is my configuration here. This is my configuration here, different addresses. I do a load here where I'm supposed to do reads. I just need to get the right number of zeros. Yeah, there you go. I have to do a load here at the other guy address, which is 800. 1, 2, 3, 4. Aha, nothing happens, okay? If you get this, you get the whole story. Now let's send messages. Okay, I send a message to zone 2, and the message is RISC-V. Oh, there it is, the message. No shared memory, ever. Bad thing, sharing memory. Don't share, okay? Now, let's send a little bit more meaningful message. I think it's zone 4, right? And if the message is Ah. It's alive. It's a toy, right? It's just for fun. But if we send a little bit more interesting message, this is the whole thing. I have a safety critical thing, can be multi-billion-dollar whatever thing, depending on this thing. I have a link which goes wherever it goes. It's Ethernet. Hey, it can go routed over whatever media link you want. I have 4 pieces in this system. One that is critical, some that are exposed to remote attacks, some that are not. And here what I'm going to do, I'm going to completely kill one of these zones, okay? And the way we kill is by restarting it, which jumps at the very first address. And nothing happens to the rest of the system. Hello, yeah. Okay, so do you want to share? Okay, so this completes, I think, almost perfectly on time. It stops once it gets the home position. It's a toy, has no feedback. If we stop it anywhere else, we don't know where the motors are, okay? So now you stop. Any final thought? Any final question? Okay. Thank you. We'll stay here a few more minutes if you are interested in a one-on-one or hard questions that you don't want to share with the audience. Thank you again for coming. Thank you for being part of the big RISC-V family. It's really great to see more people every year, more interest, more real companies, more real projects, okay? So see you next year.
Thank you.